Okay, good evening everyone. Start with today's class, and today we are going to discuss questions for week 7. So today I have 12 questions which we are going to be discussing, and yeah, I can see some questions by Shanmukha Priya. So Shanmukha Priya, I have not gone through, I don't generally go through the current year assignment questions, but now that you have asked the doubt, I'll go through it and I will let you know next week. And you had some questions which you asked me previous week. I have prepared them. We will discuss it at the end of the class. Okay? And in the discussion forum, as current year assignments are not my part, generally discuss. Have to wait for the reply from sir. But this first question which you said last week's numerical, I'll check it. Should be the correct answer, but you can again raise that raise the question for this answer as well in the discussion forum. I think it might be late, but you will still get a reply. Okay, so we will start. Not wait for time. Yeah. So today we have 12 questions. After that, we will discuss two questions which was a doubt by one of you. Okay, so one numerical is there and one question is there. So those two questions we'll discuss at the last. The rest is 12 questions you have. I hope everyone knows the rules for the class. Please keep yourselves mute for the audio and the video throughout the class. And if you have any kind of doubts, please ask in the chat box. I will be watching it continuously. Okay. And the second thing is you will be given around 2 3 minutes time for each question. Think properly and answer whatever you think is correct in the chat box. Okay, so that's it. So we'll start with the first question of today. So here I have mentioned the slide numbers from the lecture material. If you have any doubt, you can always go back to the slides present in it and check again. Okay, so that's why the slide numbers are mentioned as well. Which of the following microorganisms is most commonly used for large-scale citric acid production? Penicillium citrinum, Aspergillus niger, Corynebacterium species, Mucor piriformis. So start answering and keep noting down how many correct answers and how many wrong answers you all are giving. Okay, we will check your scores at the end of the session. So start. Let's see what is the correct answer. It is B, Aspergillus niger. So, although several microorganisms like Penicillium candida and Mucor performance can produce citric acid, industrial scale production predominantly uses Aspergillus niger due to its high yield. All these produce citric acid, but in a large scale, it is only the B option, that is Aspergillus niger, is used as it gives high yield compared to the other microorganisms, and it requires simple nutrients. The cultivation is easy and negligible byproduct formation. Doesn't the byproduct formation doesn't need that much of attention of yours to mm, keep seeing if things are working properly or not. So it can grow very well with less amount of nutrition and easy cultivation methods. That's why Aspergillus niger is commonly used for large scale citric acid production. Moving on to the next question, in citric acid production, optimal iron concentration is maintained at 0.5 to 1 ppm, 0.05 to 0.5 ppm, 1.5 to 2.5 ppm, 2.5 to 5. Start answering. Okay, let's see what is the correct answer to this question. It is B. 0.05 to zero point 0.5 ppm. So iron is a cofactor for aconitase, an enzyme in the TCA cycle. I hope everyone knows what is the TCA cycle, what is the byproduct in the TCA cycle, what happens. I guess that is known by everyone. This is a basic thing. Okay? Too little iron inhibits enzyme activity, whereas too much increases unwanted byproducts like oxalic acid. Therefore, maintaining 0.05 to zero point 0.5 ppm iron optimizes the citric production. So, the optimal iron concentration is this much. Either too much iron or very less iron can lead to the production of unwanted byproducts like oxalic acid. But the byproduct which we need is citric acid. So, for that, levels of iron has to be balanced. So the balanced concentration required is 0.05 to zero point 0.5 ppm. Okay, I hope this is clear. The next question. During citric acid fermentation, a pH higher than 4 leads to accumulation of gluconic acid, oxalic acid, succinic acid, lactic acid. Start answering. Okay, if there is emergency, you can join this class and you watch the YouTube. Okay, let's see what is the correct answer. It is A. Gluconic acid. So during the citric acid fermentation, a pH higher than 4 leads to accumulation of gluconic acid. So pH higher than 4 is not suitable for citric acid fermentation, hence it leads to unwanted byproducts like gluconic acid. So the ideal pH for citric acid transport is pH equal to or less than 2.5. pH more than 4 leads to gluconic acid accumulation, and pH more than 6 leads to oxalic acid predominance. And thus, the pH control is critical to maximize citric acid yields and minimize unwanted byproducts, as I told, right? So, moving on to the next question, which fermentation method accounts for 80% of global citric acid production? Solid state fermentation, surface culture fermentation, submerged fermentation, immobilized cell fermentation. Start answering. Okay, let's see what is the correct answer to this question. It is submerged fermentation. So, submerged fermentation in stir tanked and airlift bioreactors dominates industrial citric acid production because it provides better oxygen transfer, higher yields, easy process control, and continuous production feasibility. So, it was asked which fermentation method accounts for 80%, like the highest amount of global citric acid production. So that is done through submerged fermentation in a stirred tank. We have discussed about the stirred tank and airlift bioreactors in the previous weeks. So this is what is used for citric acid production because it gives better oxygen transfer, higher yields, easy process control, and continuous production feasibility. Moving on to the next question. In citric acid submerged fermentation, which morphology of Aspergillus niger gives maximum yield? Free dispersed mycelia, forked bulbous hyphae forming pellets, highly branched filamentous mycelia, thin loosely aggregated hyphae. Start answering. Okay, let's see what is the correct answer to this question. It is B. Forked bulbous hyphae forming pellets. So pellet-like growth of Aspergillus niger allows for better oxygen transfer, reduced broth viscosity, less shear damage. Hence, this morphology is preferred for high yield citric acid production. So, there are various types of morphology present for the Aspergillus niger species. So, the one which is really helpful for the citric acid submerged fermentation is the bulbous hyphae type, which is like a round kind of shape and which forms pellets. So this is good for the better oxygen transfer, reduced broth viscosity, and less shear damage. That's why they prefer this kind of morphology for the high yield citric acid production. Moving on to the next, during downstream processing of citric acid, calcium citrate is precipitated by adding H2SO4, calcium hydroxide, Na2CO3, NaH, NH4OH. Start answering. Okay, let's see what is the answer to this question. It is B. Calcium hydroxide. So, adding calcium hydroxide neutralizes the citric acid fermentation broth at pH nearly 6.8, forming insoluble calcium citrate, which is later treated with H2SO4 to release pure citric acid. So, first, what is done? That calcium hydroxide is added to the citric acid fermentation broth to neutralize the pH to around 6.8 to form the insoluble calcium citrate. Then later in that sulfuric acid, which is H2SO4, is added to release the pure citric acid. This is how the downstream processing of citric acid is done by using um, calcium hydroxide and sulfuric acid. Okay. Moving on to the next question, in lactic acid production, which pathway is used for homofermentative lag? Pentophosphate pathway, enter Dodroff pathway, Embden-Meyerhoff-Barnes pathway, and TCA cycle. I hope you all are clear with all these pathways. These were there in the lectures and you should be thorough with it. You all must have learned at the plus 2 level as well. Okay, let's see what is the correct answer. It is C, EMP pathway. So the homofermentative lactic acid bacteria, example L. bulgaricus, L. delbrueckii, convert 95% of sugars into lactic acid through the EMP pathway, producing 2 moles lactate per mole glucose. So, what was the question asked? In lactic acid production, which pathway is used for homofermentative lab? So, lab is lactic acid bacteria. So, that is the EMP pathway. It converts 95% sugar into lactic acid through the EMP pathway, which this homofermentative lactic acid bacteria giving at last 2 moles of lactate per mole glucose. Right? Moving on to the next question. Which of the following lactic acid bacteria are heterofermentative? Lactobacillus delbrueckii, Lactobacillus bulgaricus, Lactobacillus acidophilus, Lactobacillus casei. Start answering. Okay, let's see what is the correct answer to this question. It is C. Lactobacillus acidophilus. So, homofermentative lab, that is the lactoacid bacteria, converts sugars to lactic acid that we discussed in the previous question. They also produce lactic acid plus ethanol plus carbon dioxide plus acetic acid via the pentose phosphate pathway. So, the lab which is the lactic acid bacteria in these questions in these points is the lactobacillus acidophilus, which is the prime heterofermenter. Okay, moving on to the next question. What is the optimal range temperature range for lactic acid fermentation using L. bulgaricus? So it is 20 to 25 degrees Celsius, 28 to 32 degrees Celsius, 45 to 50 degrees Celsius, or 55 to 60 degrees Celsius. Start answering. Okay, let's see what is the answer to this question. It is C, 45 to 50 degrees. So different strains have different optimal fermentation temperatures. So for Bulgaricus it is 45 to 50 degrees. For L. Debrucki it is nearly 45 degrees. For L. Casei it is 30 degrees. So here, as in the question, we can see for L. Bulgaricus and L. Delbrucki the temperature is almost similar. So here I have made the correct answer as C. Samely in the assignment, sometimes we think round figure as something, but the professor has thought of a round figure as something, and there can be little bit differences in the choice of answers. So yeah, that question I will again check as to why it's done like that. Okay. Moving on to the next question. Why is calcium hydroxide added intermittently during lactic acid fermentation? To maintain anaerobic conditions, to prevent protein denaturation, to neutralize lactic acid and avoid inhibition, to increase sugar conversion. Okay, let's see what is the correct answer. It is C. To neutralize lactic acid and avoid inhibition. So, accumulation of lactic acid decreases pH and inhibits microbial activity. Calcium hydroxide slurry maintains the acidity below 0.1%, ensuring shorter fermentation time, higher yields, and stable microbial growth. So, the question was why calcium hydroxide is added intermittently, like in breaks during the lactic acid fermentation, because the accumulation of lactic acid decreases the pH, and we already read that the balancing of pH is very important, otherwise there can be unwanted products. And if the pH decreases due to lactic acid accumulation, it can inhibit the microbial activity, microbial growth, which is required for fermentation. So calcium hydroxide slurry maintains the acidity below 0.1%, ensuring shorter fermentation time, higher yields, and stable microbial growth. So that's why option C is the correct answer, to neutralize lactic acid and avoid inhibition. Inhibition means inhibiting the microbial activity. Moving on to the next question, which material is least suitable for constructing lactic acid fermenters? It is stainless steel, silver, nickel, or copper. Start answering. Okay, let's see what's the correct answer. It is copper. So the material which is least suitable for lactic acid fermenters is copper. So lactic acid is highly corrosive. Thus, fermenters are built from corrosion resistant materials like stainless steel, silver, nickel alloys, or tantalum. So copper and chrome steel are highly unsuitable due to rapid corrosion. Even in our daily life, when we are using some kind of milk products, it is advised that we should not use copper containers, as it can turn into a different kind of taste and smell. You all must have faced it at some point. I don't know, but I have faced it myself. So copper is not something which we should use in for the milk product. It's the least suitable one for the lactic acid fermentation as well. Okay. Moving on, today's last question. Which of the following is a biodegradable polymer produced from lactic acid? Polyethylene terephthalate, polylactic acid, polyvinyl chloride, polystyrene. Start answering. Okay, let's see what is the correct answer. It is B, polylactic acid. So polylactic acid derived from lactic acid is a biodegradable polymer used in food packaging and the medical implants and bioplastic manufacturing. It naturally degrades into carbon dioxide and water under composting conditions. Yeah, so polylactic acid is a biodegradable polymer produced from lactic acid. That was the question, and it is also used in these things. It naturally degrades into carbon dioxide and water under composting conditions. So, as it does not leave any unwanted byproducts, it is a biodegradable polymer, right? So, this was it for today's questions. Let's first see your scores, then whoever wants to leave, they can leave, and I will clear doubts of Shanmukha Priya, which she asked last week. First, let me know your scores if anyone wants to say. Out of 12, what is your score? 9 out of 12. Okay. Scope for improvement. Anyone else? I guess everyone else is having like 100% clarity in everything. No doubts at all, huh? I'm not just talking to the one who are watching through the live session, but also through the YouTube people who are watching the recordings. To them also I have this question that are you all clear with everything? There are no doubts. I don't think it is possible. It's like a difficult subject, I guess, for understanding every bit of it without any video lectures. So, if you are still facing any kind of issue, you should definitely contact either through the YouTube comments or join the live session and ask me here. Okay? But do not stay like that. It will only um, lead to a lot of confusion during the exam, right? Okay. So, I guess only Shanmukha Priya has shared her marks. Other people don't want to share it and they can leave as well if they are not interested in listening to the doubts. Okay, so the first question, Shanmukha Priya, you asked was this one from week 1, ninth question. Uh, can you tell me by yes or no, is this the question you were asking for your as a doubt? Okay. So the question was the intermediates of glucose conversion to ethanol by yeast is pyruvate and oxalate, pyruvate and 2-acetaldehyde, pyruvate and acetaldehyde, none of the above. So the accepted answer given was B, pyruvate and 2-acetaldehyde. So let's see how this is the answer for this question. So first we have to understand the process of alcohol ethanol production, right? Because the question was the intermediates of glucose conversion to ethanol. So ethanol is being produced by yeast. So let's first understand that process. So here you can see 1 minute. Question is not one. Yeah. So here you can see the step 1 is the conversion of glucose to ethanol by yeast is called the alcoholic fermentation, which is carried out by the yeast, which is the budding yeast, that is Saccharomyces cerevisiae. So the overall reaction is this is glucose, right? C6H12O6 leads to C2H5OH, which is ethanol, plus 2 carbon dioxide plus ATP. So step 2 is what are the steps in this ethanol production. This is the overall reaction. If we go in the detail, first is glycolysis. I hope you know the all the steps of 10 steps of glycolysis I have not written here. It is first, the byproduct is 2-pyruvate. Glucose is converted to 2-pyruvate, and this occurs via the EMP pathway. We just discussed, right, about the EMP pathway. Then the step 2 is decarboxylation, in which pyruvate is converted to acetaldehyde plus carbon dioxide, and the enzyme involved in this reaction is pyruvate decarboxylase, and the cofactor is TPP. Next is the reduction, in which what happens, acetaldehyde is converted to ethanol, and the enzyme used is alcohol dehydrogenase, and the cofactor here is NADH is uh, converting to NAD plus. So here in some books it is written why option B is correct and why option C is not correct. Why the difference is acetaldehyde and 2-acetaldehyde, right? So in some books 2-acetaldehyde is used to indicate that two molecules of acetaldehyde. Here it is given that the two molecules of acetaldehyde are formed per glucose molecule. Per glucose molecule, two acetaldehyde molecules are formed. So the pathway clearly involves pyruvate and acetaldehyde as intermediates, and finally then ethanol production is happening, and this generates two acetaldehyde molecules. That's why I think the option given here is pyruvate and 2-acetaldehyde is correct. But conceptually somewhere this is little bit controversial. It could have been also C, that is pyruvate and acetaldehyde. Conceptually it is correct, but the question specifically expects 2-acetaldehyde to highlight the stoichiometry. Specifically if we go, it can be 2-acetaldehyde as well, and maybe sir, the professor, he has, according to him it is 2-acetaldehyde, because in some books it is mentioned as 2-acetaldehyde. So there is some kind of discrepancy, and I can understand that why it was confusing for you, but yeah, that is the answer. Okay. uh was it could you, in the slides yeah, it is 2-pyruvate. Yeah, I have missed it. I have it 2-pyruvate, right? Glucose is converted to 2-pyruvate. Here I have missed 2, right? Yeah, 2-pyruvate will give 2-acetaldehyde, right? So that is correct. But in option it was missing. Okay, I understood. Yeah, but if we check, it is like 2-pyruvate leads to 2-acetaldehyde, because 2-pyruvate was missing in the option, so you got confused. I can understand that. Yeah, maybe that was wrong in that part. But because the what's the question here? The intermediates should be 2-pyruvate and 2-acetaldehyde. This option has been given wrong, I think. Yeah, but pyruvate and oxalate is not correct, and pyruvate and acetaldehyde is not correct because both of them are not true. Maybe it should have been none of the above actually. I don't know why the accepted answer is B. Like, this is not my thing. You can ask it in the forum. I don't know. They were going to make it D, and they have written it B here, or they have missed the 2-pyruvate here. Not sure. Yeah, yeah. So, okay, Shanmukha? Yeah. I can understand that. 2-pyruvate and 2-acetaldehyde is the correct answer. Either in B, they have missed 2 the pyruvate, or it should be none of the above. That's very nice of you to point it out. I don't know why others have not done it. But yeah, try to mail to sir once to ask him if this can be corrected, because it carries marks. So I am worried about that thing. Or else just write it in the discussion forum. I'm not sure if he's. I think in middle there was one live session with sir, right? If you have attended it, you could have asked it directly as well. If there is any kind of live session happening with the professor anytime, please do attend it so that you can clarify your doubt, because these doubts can only be clarified with him, right? Yeah. Did you ask him there this question? But next time if it happens, try to ask these doubts which you had, because I think this is a valid point. The answer given here is not correct. Okay. Okay, then the next question was this, what's the numerical, right? What was your doubt in this? Can you tell me? Because I can explain the whole numerical to you, but I'm not sure if you have doubt in the solving of the numerical, or if do you think this question also doesn't have a proper correct answer? Tell me, what is your doubt in this question? Yeah, I'm waiting. Problem? Check and tell me. I tried with formula given in slides, ma'am, but I didn't get the answer. Batch reactor formula. Okay. Can you give basic outline or steps? Okay. Let's see. I have tried to include it here. So yeah. So these are the given things, right? Initial glucose, which is S S naught is equal to 1000 gram per liters, or it is 1 kg per liter. The degree of, so okay, first let me read the question for you. So glucose is to be converted into fructose by using glucose isomerase enzyme. The initial glucose concentration is 1000 grams per liter. The degree of conversion is 75%. Calculate the volume of the batch reactor needed to produce 100 kg of fructose per day by glucose isomerase enzyme. The Vmax is equal to 2.5 kg per meter cube per second, and Km is equal to 6 kg per meter cube, and the downtime is 4 hours, and the yield is 0.8 kg per kg. Okay? Yield is per kg substrate. Okay, so the meaning is 0.8 kg per kg substrate is the yield. So they have asked to calculate the volume of batch reactor needed to produce 100 kg of fructose per day by glucose isomerase enzyme. So let's see first what is the given things here. The initial glucose is 1000 grams per liter, which is 1 kg. Degree of conversion is 75%. So here SF, which is the residual glucose, the formula given for residual glucose is 1 minus X into S naught, which is 0.25 kg. Like the degree of conversion, if we put here is 75%, we can get the, and S naught is known to be 1 kg per liter. So SF, which is the residual glucose. Okay, the residual glucose is 0.25 kg. So from these two values, that is S naught and X, we can calculate SF. So we have done it here. Then the Michaelis-Menten reaction, which is substrate is equal to Vmax substrate RS is equal to Vmax substrate by Km plus S. Then for this Vmax is given, Km is given, downtime per batch is 4 hours, and the yield, that is Yp by S, is equal to 0.8 kg product per kg substrate. And the target is 100 kilograms fructose per day. This is the question asked. So first we will calculate the batch time to reach this much conversion, that is 75%. So this is the formula. T is equal to, for the integrated for a batch reactor. I think this formula must be given in the slides, but this is the correct formula. T is equal to S naught minus SF plus Km to ln S0 by SF by Vmax. So everything we will put in the value. Ln 4 you have to calculate, you can check using a calculator, the value will come to this much, and finally we get the result as 0.0843 hours. So the batch time to reach 75 conversion is 0.0843 hours. Next we have to calculate what is the batches per day. So for that is cycle time. Cycle time is equal to T, which is the batch time, plus downtime. So we will do that. Then we will get the cycle time is 4.08 hours. Then we have to calculate batches per day. So per day we have 24 hours divided by the cycle time is equal to 5.876. This is the batches per day. Now we have the batch time and the batches per day. Finally, we have to calculate the product formed per batch. So first is at 75% conversion, the residual glucose is 0.25 kg. We already calculated it here. Then using the given yield, that is 0.8, right? Given yield is 0.8 kg product per kg substrate. So for that, if we put the P batch is equal to yield into S, that is 0.8 into 0.25 is equal to zero point 0.2 kg per liter. So the daily fructose per liter is zero point 0.2 into 5, that is the batches per day. This is the yield, that is your product batch plus the batches per day. This is the product batch plus how many batches we are making it. This is for one batch, and these how many batches we have to make, that is 5.876. So it is the daily fructose per liter is 1.175 kg per liter per day. So finally we have to calculate next is the reactor volume for 100 kg per day. So volume is equal to 100 kg divided by the daily fructose per liter is equal to 85.1 liter. In the option it is given 85.47, round figure. So the match option is, yeah, A, right? Was it clear? Sure. It was a different formula. So you used any different formula to solve this question? Okay, you are saying in the slide a different formula is given, but this formula also you can use. Yeah. Okay. Good. So if you have any other doubts, I can check for you. Just let me know anything is there. In first you said something. There was only one. Which was okay. This one I will check. Last week means week 6 you are saying, right? That I will check and answer you in the next class. Other than that, if you don't have any doubt, we can disperse. Okay? And keep writing in the discussion forum. Doing masters lately, is it good or bad? Lately, in the sense you have a gap after BSc, or are you in BSc now? Gap of 5 years after BTech. Okay, so yeah, okay. So now you're doing your masters, right? So after that, I'm not sure what are your plans. If whatever it is, either you want to go for a job, if you want to do PhD, obviously the 5 years of gap is a bit much. So they may ask you what you did in those 5 years. If you can answer that intelligently, smartly, that if you can justify what in the gap period what you were doing for your career growth, something, or you can say that I was brushing my skills on this anything, then maybe it can cover it up. But yeah, I don't think I have seen people who have taken a gap but are still in good position. So uh, yeah, I understood that is the situation for many people. So uh, always say I was preparing and I needed clarity in my mind what I really want. And now that I have gained that clarity, I want to pursue in this direction. These kind of answers help rather than saying in a negative direction that I was preparing and hence I didn't join anywhere. Okay, but I don't think that will be a demerit uh, if you are good in other things like your marks and masters and your project work. Everything is good, then that is a secondary thing. Okay, you will never be pushed back only because you had a gap. Many people have gaps and still they are chosen, they are in places, so there is nothing to worry about. Yeah. Okay. Okay. Thank you, Shanmukhpriya. We'll meet week 5, 20th question. Okay, I'll check that. Okay. Correction. Okay. I'll check into it. Week 5 we will discuss next week. Week 5, 20th question we'll discuss next week. Okay. Okay. Bye.